All right, let's dive into one of the most fundamental stories in all of chemistry. It's a tale of two opposing forces, a constant push and pull that's happening all around us, and believe it or not, even inside of us. This is the story of acids, their opposites, bases, and what happens when they finally meet, salts.
You know that feeling, right? When you bite into a lemon and your whole face just puckers up? Or how soap feels so slick and, well, soapy? That's not random. It's our first clue in this chemical mystery. These sensations are the direct result of that classic rivalry between acids and bases. So let's get formal and properly introduce the two main characters in this chemical drama. In one corner, we have the acids, and in the other, their sworn chemical enemies, the bases. We can actually tell these two apart with some pretty simple detective work. Acids, for one, have that trademark sour taste, and if you have some litmus paper, they'll turn the blue paper red. Bases, on the other hand, are the total opposite. They tend to taste bitter, feel slippery or soapy, and they turn red litmus paper blue. You see? Perfect opposites.
So what's really going on at the microscopic level? What gives an acid its acidness? It all comes down to this little fellow right here, the hydrogen ion, or H+. When you pop an acid into water, it basically lets loose a ton of these hydrogen ions. That is its defining move.
And in the other corner, we've got the bases. What's their signature move? Well, they release hydroxide ions, or OH- in water. So you've got acids giving away hydrogen ions and bases giving away hydroxide ions. This is the core conflict that drives all of their chemistry. But here's where it gets even more interesting. Just like characters in any good story, not all acids and bases are equally powerful. Some are really strong and others are pretty weak. And this isn't just about how dangerous they are, it's all about their chemical behavior.
Okay, so the key is how they act when they hit the water. A strong acid is like a floodlight. The moment it's in water, bam, it completely splits apart, or ionizes, releasing all of its hydrogen ions at once. A weak acid, though, is more like a dim little nightlight. It only splits up a tiny bit, releasing just a few of its hydrogen ions. And you know what? The exact same idea applies to strong and weak bases with their hydroxide ions.
Let's put some names to these faces because you already know a bunch of them. That hydrochloric acid in your stomach? That's a strong acid. But the acetic acid that gives vinegar its kick, or the citric acid in a lemon, total weak acids. On the base side, sodium hydroxide, the stuff in powerful drain cleaners, is super strong. But ammonium hydroxide, which you might find in a household cleaner, is a weak base.
All right, so we've met our players, we know their power levels. But what happens when these chemical opposites finally come face to face? This, my friends, is where the action really starts.
Now, you might expect a huge chemical battle, right? But what actually happens is more like a truce. The H+ from the acid and the OH- from the base find each other and combine to make plain old water. And the other pieces that are left over, they get together to form a whole new thing called a salt. We call this a neutralization reaction.
The source material really puts it perfectly. In these reactions, both the acid and the base lose their character. The acid isn't acidic anymore, and the base isn't basic anymore. Their defining powers are just gone. They've neutralized each other.
Now, while neutralization is kind of their main story, acids do have a few other tricks up their sleeve. For example, if you mix them with certain metals, they'll produce flammable hydrogen gas. Or if you mix them with carbonates, think of something like an eggshell, they'll start fizzing and produce carbon dioxide gas. That fizz is the reaction happening right before your eyes.
Okay, so that neutralization reaction left us with something new. Let's zoom in a little closer on the result of that chemical truce, the salts. So when I say salt, your mind probably jumps to the shaker on the dinner table, right? And you're not wrong. But in the world of chemistry, salt is a much bigger category. It's basically any compound that's formed when an acid and a base cancel each other out. It's built from the leftovers, the positive piece from the base and the negative piece from the acid.
Now let's talk about the most famous salt of all, sodium chloride, aka common table salt. You might think its only job is to season your food, but it has this whole secret identity. In the industrial world, it's the starting block for an entire family of super important chemicals.
It's all done through a process with a kind of fancy name, the Chlor-Alkali process. But the idea behind it is actually pretty simple. You start with brine, which is just really, really salty water, and you pass an electric current through it. That's it. That jolt of electricity breaks everything apart and gives you three incredibly useful chemicals: sodium hydroxide, chlorine gas, and hydrogen gas. And just look at what we can make from there. That sodium hydroxide is a key ingredient for making things like soaps and paper. We can also create baking soda, for baking, or for calming an upset stomach, and washing soda, which is used in detergents and for softening hard water. And all of it, every single bit, starts with simple table salt. Pretty amazing, right?
So, we've talked about acids and bases being strong or weak, but that's a little bit vague. How do we measure their strength precisely? To put a hard number on this chemical power struggle, we have one final, crucial tool, the pH scale.
Think of it like the ultimate scorecard. It tells us exactly where any given substance falls on that whole spectrum from acidic to basic.
The entire scale is balanced right in the middle, on the number 7. If something has a pH of 7, it is perfectly neutral, not acidic, not basic, just neutral. Pure water is the classic example here.
From that neutral center, the scale moves in both directions. Anything with a pH less than 7 is acidic, and the lower the number gets, the stronger the acid. Anything with a pH greater than 7 is basic or alkaline, and the higher the number, the stronger the base. Simple as that.
And I promise this isn't just some abstract thing for a chemistry lab. We use our knowledge of pH all the time. Farmers test and adjust the pH of their soil to grow healthier crops. When you take an antacid, you're using a base to neutralize extra stomach acid. Even your toothpaste is slightly basic to fight the acids that cause cavities. And yeah, when you put baking soda on a bee sting, you're performing a little neutralization reaction right on your own skin. So you see, from the chemistry inside our own bodies to massive global industries, this constant dance between acids and bases truly defines our world. It's this fundamental chemical balance that, once you start looking for it, you'll realize is absolutely everywhere. So the only question left is, where are you going to see it next?